Hello everyone and welcome back to this online NPTEL course on aquatic geochemistry. We had been discussing freshwater resources and its composition till now, and in this particular module starting today we will be discussing about the seawater composition and the ocean composition. So, as you all know that the oceans, they are vast and they hold some very important they are extremely important for life on earth. Okay, they are of immense importance in every way in terms of life. Having said that, that life started in the oceans, managing climate, then maintaining all the earth's processes happens through this extremely important reservoir oceans. Okay, so oceanography is a very vast subject. Oceanography is a different subject itself, and it's a huge subject. It has multiple divisions. In oceanography you can have physical oceanography, people who are just working on the physical aspects of the ocean. Then there separate is the chemical oceanography group, who works just on the chemistry and the composition of water. Marine oceanography is again a very different branch, and similarly there are multiple branches in these top three branches. So, physical oceanography, chemical oceanography, biological oceanography. In this three big groups, again you can have small multiple groups that work on very specific problems. Now, the issue with the oceans is that accessibility, how accessible are the oceans? For instance, when you are on land, if you are working on a small system like a lake system or a river system, the boundaries, how much you need to expand your sampling, how much you need to do. In the oceans, it's very different, right? The ocean is entirely moving, it's mixed. So, when you need to take a data, you have limited accessibility to the coast. So, initially when when oceanography started, then it was the data sets were very few, and there were a lot of blockages came because most of the areas were inaccessible, like the seas are very difficult to go, to stay, to do some experimental activities, to measure data. Slowly with the invent of more and more technologies, our understanding of the oceans have increased several times. So, it is a very rapidly growing field, and since the 1900s, a lot, every year there has been just new and new discoveries happening, be it in terms of in terms of how life has created, how things have evolved, and how it's still we are discovering new and new species every day, it is said. And in terms of chemistry also, the processes, many processes, we still do not understand that why the data behaves like the way it does. So, still a lot of people, they are trying to do experiments, the data is required, long term data is required. So, many many current research activities are ongoing, and in fact, it is said that we have more understanding of the space as such than the oceans. I mean, it is that unknown. So, what we have just seen the surface, in terms of knowledge, we have just touched the surface of that knowledge, that is happening, what things are happening in the oceans. And they play a huge role in earth science, in in all the global biogeochemical cycles, in terms of in terms of maintenance of earth's climate, in terms of evolving life, and evolving the how matter and energy and everything is flowing across the different spheres. So, if you look at the vastness of it, you will see that understanding things become very difficult. So, let us look into a few numbers first. Okay. So, we will start with the huge, when we talk about, as I every time say, that when we are going to understand the chemistry, we first need to understand, okay, where is this water coming from. Okay. Let us just make this ocean empty. If I have to make the ocean empty, where will this water come from? So, the volume of the oceans is 1.37 into 10 to the power 21 liters. Okay. All the rivers combined together, we have this number 3.74 into 10 to the power 16 liters. Okay. More in volume comes from the rainfall that happens, again, that is 3.8 into 10 to the power 17 liter, and from hydrothermal vents also we have 1.7 into 10 to the power 14 liters. So, as you can see that rivers and hydrothermal vents are the only external sources. It is not even truly external, because most of the rivers are also rain fed. So, this rain is again coming from the water mass that has evaporated from the oceans themselves. So, basically most of the rivers and the rain on the surface, that is entirely the ocean recycling itself. So, this is just basically the recycling of the ocean water itself. The only external source being hydrothermal vents, and that is also not truly external. What do I mean by external? External meaning outside of the ocean system, but it is not so. What happens is, through the cracks and in the oceanic crust, there are multiple cracks developing because of tectonic movements, the plates stretching and all, and also because of magmatic activities. There can be plate thinning and the cracks go in, and if there is an magmatic body there, then the heat causes the volcanic like eruptions, but just that instead of volcanoes, the water that is entering the cracks again gets evaporated, and it just comes out from those vents. So, what you have on the mounds is like such kinds of mounds, mountain like creatures on top of heap like structures, and the black smoke like with heavily laden dust particles, they will come. This is not dust in the sense of dust, atmospheric dust, no, that is not like dust. It is just the reactions that is happening specifically with iron, manganese and a few other elements. Their sulfides, they look black, and therefore the these vents, they are also called as black smokers. So, essentially when we are looking into the hydrological cycle, the dominance is of the ocean water itself. It is just getting recycled, and there are various storages. It is coming maybe with some delayed time flow. For instance, the glaciers, it is just like the ocean of the past has supplied it with the snow and the ice, and now we are getting the rivers and the lakes and groundwater, everybody joining into the drainage system, the continental drainage system, and again that is finally coming into the ocean. Okay. So, it is not possible to say that the ocean was created due to the rivers and the hydrothermal vents and the rain. It is of course of the primordial hydrogen and oxygen bonding and forming water, and that is the source of the primary ocean, the primeval ocean that we had. And after the continents started forming, the continuous erosion just went on adding matter to the oceans. Oceans is our vast sink, and we are going to slowly see how things control its chemistry. But understand this, that chemical oceanography is a huge subject and a lot of processes are happening. In this particular course, I will not be able to give you an in-depth understanding, but what I will try to do is give you a few glimpses to show the directions in which research is going on, and particular important directions in which chemical oceanography is studied. And there are multiple ways that people have conducted studies, and multiple research objectives, starting from understanding the paleo ocean related to the paleoclimate, to very economic gains such as finding minerals, understanding if we can mine, what impact it will do, how much we can economically progress in that kind of field. So, the kind of studies are very vast, very different, and every element, each and every element for their geochemical cycling through the earth, the ocean is a very important reservoir for every element. Therefore, what happens is, whoever takes up a particular element, they also need to know a little bit of the ocean, okay? Because there is no element that exists only on the continent and not in the ocean. Yes, their concentration is extremely different. Yeah, the concentrations might vary and it might be difficult to get numbers in seawater, but it is getting recycled through the ocean again. So, for every element, if you come across any geochemist, you will know that they do a little bit of oceanography if they are trying to understand the geochemical cycling of the element. Okay. So, there is every element, the way it undergoes its transformations, different, it is different, and therefore, different studies are there. Okay. Now, let us look into some facts about the origin and the control of the seawater. So, the majority of the dissolved salts in ocean, they originated from the continental weathering. Okay. So, the continental weathering, they started supplying the salts and they started supplying the weather product with solutes transported specifically due to river inputs. Okay. So, the rivers, they are the largest suppliers of continental weathered products to the oceans. Okay. Seawater chemistry reflects not only riverine inputs, but multiple sources also. And what do you mean by multiple sources? So, rivers are a direct input. What are the other sources? There can be atmospheric dust. Okay. So, when wind is blowing, wind is not blowing just like nothing other than air, it is also carrying a lot of dust, it is also carrying a lot of other gases and everything. So, atmosphere is a very big source also apart from the rivers, and atmosphere, the winds that is blowing from the continental areas to the ocean, they carry a lot of continental dust, and these continental dust is equally important just as sediments are in terms of rivers. So, just like rivers are carrying sediments into the ocean, atmosphere is also carrying this dust, and this dust goes and settles into the ocean. Again, apart from atmosphere, what are there? There are hydrothermal vents. Okay. So, these hydrothermal vents are they are releasing weathered products from the oceanic crust, and also sometimes whatever is coming from the mantle, the volcanoes and all the oceanic volcanoes. Okay, the number of oceanic volcanoes are much more as compared to land volcanoes. Okay, there is continuous eruptions going on somewhere in the oceanic crust, and we do not even know about it. So, every day, every time some processes are happening which we do not even know because we are sitting far inside the land. Okay. So, these processes are continuously happening, the hydrothermal vents are continuously happening, there are volcanoes, they are continuously happening. So, there are multiple sources. Also, there is a lot of biological interactions also. So, there is a lot of pathways that is happening, and it is not just simply the rivers. Okay. A significant fraction of the dissolved continents is supplied through the hydrothermal alteration of the oceanic crust and the mid-oceanic ridges, where the seawater interacts with hot basalt. So, that kind of interaction actually makes those areas very, very rich in particular minerals, and the metals sometimes are so high in those minerals that they can actually be mined. So, that is why when we are looking into economic applications, people try to find out this kind of places where a lot of hydrothermal alterations are going on, a lot of vents are there, what kind of minerals are there. So, that is extremely contributing to the ocean chemistry. Then some components of seawater, specifically the major anions and the water itself, they cannot be explained by the weathering or the hydrothermal process. What do that mean? That means that how it is accumulating in the system, how it is mobilizing in the system, it's a continuous process which is being happening over millions and billions of years. So, the water itself, how much water came from where, that is still a question. So, some people say that this water came from the comets, from the some other comets that visited the earth, and so there are many theories. Some people say it is a mantle degassing, or the primordial hydrogen and oxygen, they the interactions happened and the water got formed. So, many times we are still asking the questions, okay, what is actually the source of this particular element, where did this element actually come from. For instance, when we talk about chloride and we say, okay, where is chloride coming from. So, for lakes, for rivers, we will say it is either some kind of evaporite rock deposits, or it will be the rainfall. Okay, so, the rain will have chloride, or some halide and evaporite deposits will be there in the geology. But these evaporite and halides, they are also coming from where? They are coming from marine deposits. So, previously these areas, they were underwater, these deposits got pushed into the continents. So, that way it got preserved in the formation, but it was produced due to marine activities, due to marine influence. So, it means that marine was already enriched with chlorides and evaporate other kinds of salts before the rock actually formed. That means the ocean is already rich with that particular element. It is not the other way around. It is not that the ocean became rich in chloride because the river started flowing with chlorides. So, again same for the rain. The rain, when it started, it may not be having as much chloride today, chloride at in the past as it has today, because the ocean is gradually getting more and more saline. So, if that is the case, like if the continents are supplying chloride, then the chloride came from the oceans. So, where is the source of this chlorine? So, those kind of questions is very difficult to explain if you are just talking in terms of weathering and hydrothermal events. So, weathering alone and hydrothermal events alone does not explain all the major ions like chloride and sulfates in the ocean. There is a lot of other processes that are happening that is going to make the seawater, give the seawater its composition that we see today. So, if you try to do those calculations based solely on weathering and river input and hydrothermal input, then you are not going to get the numbers. Okay. For instance, these constituents were introduced due to volcanic degassing. So, the volatiles that got trapped when the earth is forming, they are continuously getting released due to volcanic activities. And since these are volatiles, they are in the gaseous form. So, this process is called volatiles volcanic degassing, okay. And they were there in the ocean atmosphere system much long much prior to even most of the rivers formed. So, this is like very primitive earth, where the very primitive oceans was there, very primitive atmosphere is there, where everything is just formed, and the first few millions of years these kind of when even the crust is not as big as it is today and is not as complex as it is today. The ocean does not function as a passive reservoir where salts accumulate indefinitely. Instead, it is extremely dynamic and open system. It is not that everything comes in and just settles there. No, it is not like that. It is continuously interacting, it is losing items, it is gaining items. So, one need not think that it is always just sediments are coming and sinking. Yes, true, but some place the rocks are also getting uplifted. It is getting uplifted and attached to the continental crust. So, it is also getting removed out of the ocean system as out of the interaction. Also, when evaporation is happening, a lot of salts are getting evaporated with the water, and they are moving in the whatever in the rain. When we discussed the composition of the rain, you saw that marine salts, they are one of the largest contributor of sodium, potassium, calcium, chloride and sulfate. They are one of the largest contributors of elements in terrestrial aquatic systems. So, with the vapor, a lot of salts are also getting removed from the system, and it is again getting recycled back. The concentration of any element in seawater is governed by the balance of inputs and outputs. So, always there is some sources and some sinks. So, this is continuously happening, and we are always trying to do this budgeting. Okay. Within the ocean itself, the elements undergo continuous internal cycling through dissolved forms, through inorganic solids, through organic matter. It is just continuously interacting. Okay. And we have a particular term for that. We have a residence time for every element, and how it is changing from different from organic matter to the inorganic form. We have certain known processes that can help us understand how much time it takes for burial, for remobilization and things like that. The internal redistribution is tightly coupled to physical circulation, geological processes and biological activity. That is why this is all considered as a subject. Like if you take up oceanography, you will be studying a lot of physical oceanography, you will be studying about the climate, you will be studying about the geology, you will be studying about marine ecology also, because this internal redistribution of the elements is actually controlled by water flow, that is its physical circulation, by the geological processes, and it can start from crustal formation, weathering and very long term processes, and biological activity. Extremely important, it is extremely important for all the element cycling. Marine organisms, that is they play a central role by mediating chemical transformations. They make new products, they break down all the products, they exert a strong control over the elemental cycling and the overall composition of seawater. So, what we see in the seawater therefore cannot be directly related to only the inputs and the outputs. We have to have an understanding of the entire range of processes that is happening, and that is inorganic processes and organic processes. So, for oceanography organic processes are also extremely important, as compared to terrestrial systems, where sometimes we forget that the elements can also be having an internal cycling by the organisms, by the biota. But in oceanography, you can never forget that that is an extremely important role that the marine organisms are playing. Now, let us look into some extremely useful concepts that defines the seawater composition, and that very important. The first thing that comes to our mind when we talk about ocean water and seawater is its salinity, or how salty is the water. Its particular definition is that the weight in grams of dissolved inorganic matter in 1 kg of water, after all the bromide and iodide have been replaced by an equivalent amount of chloride and all the carbonates has been converted to its oxide form. That means, now whatever is left in that inorganic matter is only in terms of chlorides. So, if you have 1 kg of water, how many grams of salts is there in terms of their chlorides? And there will be no bromides, there will be no iodides, and all the carbonates has been removed by different processes, and that carbon dioxide has been driven off. So, that is the weight of the chloride salt. So, that is the salinity of the sample. In another equivalent, this thing is also called chlorinity, which is just the measurement of the chloride itself. So, the only halide in the sample is the chloride, and the conversion is as such. And standard seawater, like average, the seawater has a salinity of 35 parts per 1000. Okay, it is reported as parts per 1000. That is also called PPT, or it is mentioned as that per mil, the percentage with an extra 0, and the chlorinity of average seawater is 19.374 PPT. The ocean water always has a variation, they can vary between 33 to 38 PPT. Now, different seas, different parts of the ocean, the salinity may vary. In the surface water also, the salinity may vary in the first few hundred meters, but in the depth, in the deep ocean, the salinity is always the same. So, the surface ocean, depending on where you are and what kind of events is happening, that is evaporation, precipitation kind of events, what events that is happening, or if there is sea ice forming and there is freezing and such kind of events that impacts the salinity, that controls the surface water salinity. Otherwise, the salinity is very much fixed. So, here you can see the salinity gradient, and we are going to start comparing with drinking water and fresh water. In fresh water, the salinities are varying between 0 to 0.5 ppt, and on average we see it is generally around 0.1 ppt. So, that is our fresh water, that means that is very low in chlorides. Okay. So, 0 to 0.1 ppt is our normal, maximum till 0.5 ppt. For agriculture, the limit is till 2 ppt. If the water is more saline, we do not generally use that water for agriculture. So, in our previous lecture, we had been discussing about groundwater salinization, and with specifically in extensive agriculture, that becomes the limiting point where you need to have water which is good and which is suitable even for agriculture. So, if the water is too salty, it is not any use. In fact, there are questions sometimes comes that why are we thinking about water, because the earth has so much of water, and we talk about water scarcity. Why not just simply take the water and evaporate it and make fresh water out of it. But maybe in future, yes, it's a very to provide water in the scale that we use, we would need a huge it is an extra economic burden for any country. Okay. So, we do not still use ocean water directly for any purpose. Okay. Maximum for fishing, so for saltwater fishes, fisheries and all that, that is the only, and yes, of course, for salt production and for transportation, that is only, but for other purpose that water is absolutely unfit for any proper purpose. Different seas, different parts of the ocean can have different kinds of salinity, depending on how much fresh water inputs are coming in, what is the climate there, how much rainfall is happening and all. So, different seas you will note that has different kinds of salinity. So, Baltic Sea has 8 ppt, Black Sea has 18 ppt, the Mediterranean has 38 ppt, while the Red Sea is very salty, 40 ppt. Okay, so, the salinity of different seas can have very can vary. Now, what is important to understand is that its composition, the seawater composition is extremely controlled by the oceanic currents, that means its physical the physical circulation, its currents. Now, apart from salinity, what is important is ocean temperature. Okay. Now, temperature and salinity, both of this determines the density of seawater. So, temperature and salinity, they are key parameters that decides the flow and currents in the ocean. Now, why is temperature different? That is because the earth is tilted at an axis and earth's surface is not the heat transfer from the from the sun is not equal at every region. So, due to the unequal heating of the earth's surface and of the atmosphere, there is certain atmospheric circulation which again has an effect on the ocean circulation. So, the unequal heating of the earth causes the atmospheric circulation. Okay. So, we have what is called these kinds of cells that forms on the planet. So, the equatorial region has these kind of Hadley cells, then there is Ferrel cells in the temperate regions, and there are polar cells in the polar region. So, this is due to two main factors. First of it is the insolation and unequal insolation. Okay. Unequal insolation at every point at that region, and second of all the Coriolis effect. Okay. The Coriolis effect. What is the Coriolis effect? Now, the earth is tilted and the earth is rotating on its axis, and due to its axis, due to its rotation, there is a centrifugal and the centripetal force continuously acting. Due to the balance of these forces, what we have is this Coriolis effect. Okay. Now, I am not going to explain in details about this kind of atmospheric circulation, but what is important for you to understand is that because of unequal insolation and Coriolis effect, we have the atmospheric circulation where we have winds, winds have currents, it is going deflected to the right. In the northern hemisphere, it gets deflected to the left. In the southern hemisphere, it moves in in long ranges. So, this winds also affects the water. So, here is an example of how water currents get made, and this process is called the named after the scientist who discovered it, named actually by Ekman. It is called the Ekman current. So, what happens is if the wind is blowing, then the water also gets dragged with the wind, and due to Coriolis effect it starts to move right in the northern hemisphere. So, if the wind direction is like this, then due to Coriolis effect the surface current starts having a slight angle and it starts moving like this. It just gets dragged with the wind. Okay. Let us call this effect as the dragging due to the frictional forces and viscous forces within the water masses. What happens is then layers get created. Okay. These layers again start. So, if this was the initial wind, this is the first layer that gets created. Now, the next layer again starts moving a little at an angle, then the next layer again starts getting moved at another angle, and as we go down in depth, okay, till a certain depth there is continuously there is a continuous shift. It is like a spiral. So, what happens is due to the spiral, if the wind is moving in this direction, the net water transport that is seen is at a right angle. Okay. Due to the spiral, the water moves in this direction. Okay. And after a certain depth, there is no movement, there is no water motion after a certain depth. So, after this depth, there is no motion beneath this. So, it is not that the entire ocean water is moving, it is only the surface ocean that is moving, and that depth is always pre-calculated. So, ocean currents, this is the how ocean currents are formed, that is when the wind is moving, the Ekman current is created and Ekman spiral is created, and these spirals are generated at each and every depth, and the final water mass is moving at a right angle to the original wind direction. This is how water is circulated over the oceans. Okay. Now, temperature and salinity and also therefore density, they are conservative properties of water. That means, they change only at the surface, at depth they are the same, they are very well mixed at depth. Okay. They are conservative, only changes are noted at the surface ocean. Below the surface ocean, in the depth of the ocean, it is all very well mixed. The density of seawater is 2 to 3% greater than the pure water. So, seawater is slightly more dense. Okay. At an average salinity of 35 ppt and temperature of 20 degrees centigrade, the density is 1.0247 gram per cc. So, that means as compared to pure water, it is just 247 0.247 gram extra. And when we report density, it is reported in this term in this symbol sigma, and of course, again it is reported in terms of 1000. So, if the density is 1.0247, then sigma becomes 24.7. Okay. So, it is 1000 times the difference between the density and the pure water density. So, that is how it is reported. Now, with this I am going to stop today, and we are going to discuss more about ocean and its composition in the next lecture. Thank you.